Welcome! In this session, we'll explore problem number 1963, titled Minimum Number of Swaps to Make the String Balanced. This is an interesting problem that challenges our ability to manipulate strings efficiently. We'll dive into the problem requirements, analyze potential approaches, and ultimately derive an optimal solution. Let's get started. In this problem, we are tasked with making a given string of brackets balanced using the minimum number of swaps. The string, which is zero-indexed, consists only of the characters and. A balanced string must satisfy one of three conditions. First, it can simply be an empty string. Second, it can be formed by concatenating two balanced strings, which we represent as AB. Lastly, it can be surrounded by a pair of square brackets, such as C, where C itself is balanced. Importantly, we are allowed to swap at most one pair of characters in the string at a time, and our goal is to determine the fewest swaps needed to ensure the string becomes balanced. The function will take a string s as input and return an integer representing the minimum number of swaps required to achieve this balance. To better understand this problem, let's explore an example. Consider the input string s equals. The output for this case is 1, meaning that just one swap is sufficient to balance the string. Specifically, we can swap the first and last characters. After the swap, the string transforms into, which meets the criteria for being balanced. This demonstrates how strategic swaps can quickly resolve imbalances in the string. For another example, consider the input string s equals. In this case, the output is 2, indicating that two swaps are required to balance the string. First, we can swap the second character with the sixth character, resulting in the intermediate string. Then, we swap the third character with the fifth character, which gives the final balanced string. The minimum number of swaps here is 2, as no fewer swaps can achieve balance in this scenario. Now, let's look at a simpler example with the input string s equals. The output here is 0, which means no swaps are necessary. This is because the string is already balanced, as every opening bracket has a corresponding closing bracket in the correct order. This example highlights that some strings may already meet the balanced condition without requiring any modifications. As we wrap up the problem statement, it's important to consider the constraints and edge cases. The string length, n, can be as large as 10 to the power of 5, so the solution must be efficient. Every character in the string is either, or, and the counts of these characters are always equal. Edge cases include strings that are already balanced, strings requiring the maximum number of swaps, very large strings close to the upper limit of n, and minimal cases where n equals 1. Although the last case is impossible due to the equal count constraint, it is still important to account for such scenarios when designing a robust solution. To solve the problem of determining the minimum number of swaps required to make a string of brackets balanced, we considered a few different approaches. First, let's look at the brute force approach. The idea here is to generate all possible swaps and check each resulting string to see if it is balanced. A string is considered balanced if every opening bracket has a corresponding closing bracket in the correct order. Using this method, for each swap, we would validate the string by iterating through it and keeping track of unmatched brackets. While this approach is straightforward, the computational cost is prohibitively high. Generating all possible swaps takes quadratic time, and validating each string takes linear time, leading to an overall time complexity of n cubed. This makes it impractical for larger strings. Additionally, the space usage is significant because we need temporary copies of the string during these operations. The brute force approach, while conceptually simple, is highly inefficient due to its cubic time complexity. This makes it unsuitable for competitive programming or scenarios involving large input sizes. To address this inefficiency, we explored an optimized stack-based approach. The key insight here is to focus on the unmatched closing brackets, as these are the only ones that need to be corrected. Each swap can resolve two unmatched brackets, making this method significantly more efficient. To implement this, we traverse the string while maintaining a counter to track the imbalance. Specifically, we increment the counter when encountering an unmatched closing bracket and decrement it when encountering an opening bracket, which can balance a previous unmatched closing bracket. At the end of the traversal, the total imbalance gives us the count of unmatched brackets, and the number of swaps required is the ceiling of half the imbalance. This process runs in linear time and uses constant space, making it a vast improvement over the brute force method. This optimized stack-based approach is highly efficient and well-suited for this problem. It processes the string in a single pass, achieving linear time complexity, and requires only a simple counter for tracking imbalance, which keeps the space complexity constant. However, it does require careful implementation to ensure that the imbalance is tracked correctly throughout the traversal. Another approach we considered is the two-pointer technique. In this method, two pointers are used to identify positions of unmatched brackets. One pointer starts from the left and the other from the right, and they work together to locate unmatched closing and opening brackets, which are then swapped. This process is repeated until the string is balanced. Like the stack-based method, the two-pointer approach also operates in linear time and constant space, but it relies on precise pointer management to avoid errors. The two-pointer approach offers similar efficiency to the stack-based method, with linear time and constant space complexity. It is also straightforward to implement in principle. However, the need to carefully manage two pointers throughout the process can make the implementation a bit more prone to mistakes. After evaluating all three approaches, we selected the optimized stack-based approach as our chosen strategy for solving this problem. The reasoning behind this choice lies in the simplicity and efficiency of the method. By observing that the total imbalance at the end of the string directly determines the number of swaps needed, and that each swap can correct two unmatched brackets, we achieve a solution that is conceptually straightforward. The stack-based logic simplifies further into a single counter, making the implementation both elegant and robust. While the two-pointer method is equally efficient, avoiding the explicit management of pointers adds to the appeal of the stack-based approach. By selecting the stack-based approach, we ensure a solution that is both time and space efficient while maintaining simplicity in implementation. This method effectively balances the trade-off between performance and ease of coding, making it the optimal choice for this problem. It avoids the pitfalls of the brute force approach's high time complexity and reduces the likelihood of errors associated with the two-pointer technique. As a result, we achieve an elegant and practical solution to the problem of minimizing swaps to balance a string of brackets. To solve problem 1963, we need to determine the minimum number of adjacent swaps required to transform a string of brackets into a balanced string. A balanced string ensures that every opening bracket, represented by, has a corresponding closing bracket, represented by, and they appear in the correct order. Now, the key insight here is to focus on the balance property. This means that at any point in the string, the number of closing brackets should never exceed the number of opening brackets. If this condition is violated, the string becomes unbalanced. Swaps are necessary when closing brackets appear before their matching opening brackets, as seen in cases like. Instead of physically simulating swaps, we can optimize the process by using counters to measure the imbalance and directly compute the minimum swaps required. For this, we utilize two counters, one for unmatched opening brackets and one for unmatched closing brackets, along with an imbalance tracker that keeps count of unmatched closing brackets as we traverse the string. To implement the solution, we start by initializing three variables, open, close, and imbalance, all set to 0. These will help us track unmatched opening brackets, unmatched closing brackets, and the overall imbalance, respectively. As we traverse the string, for each character, we check whether it is an opening or closing bracket. If it's an opening bracket, we increment the open counter, which means we now have one more available opening bracket. Additionally, if there was any existing imbalance, we decrement the imbalance since the new opening bracket can now match a previously unmatched closing bracket. On the other hand, if we encounter a closing bracket, we increment the close counter, which means we have one more unmatched closing bracket. At this point, if the count of close exceeds open, it indicates an imbalance, so we increment the imbalance counter. Once the traversal is complete, the total number of swaps required to balance the string is calculated as the ceiling of half the imbalance, because each swap resolves two unbalanced brackets, one opening and one closing. Finally, we return the result as the minimum swaps required. Let's walk through an example to see this process in action. Consider the input string. Initially, all counters are set to 0, open equals 0, close equals 0, and imbalance equals 0. As we traverse the string, the first character is. We increment the close counter to 1, and since close now exceeds open, we also increment the imbalance to 1. The next character is. Here, we increment the open counter to 1, and because there is an existing imbalance, we reduce it back to 0, as this opening bracket balances the previously unmatched closing bracket. Moving to the third character, which is another, we increment close to 2. Since close is once again greater than open, we increment the imbalance to 1. Finally, for the last character, we increment open to 2 and reduce the imbalance to 0. At the end of the traversal, the imbalance is 0, so no swaps are needed, and the result is calculated as CL, imbalance/2, which equals 0 swaps. The algorithm efficiently determines that only one swap is required to balance the string. Now, let's analyze some edge cases to ensure the algorithm handles all scenarios correctly. First, consider already balanced strings, such as. Here, the algorithm identifies that no swaps are needed, as the string is already balanced. Next, take strings with only one type of bracket, such as or. In these cases, balancing is impossible, as there are no matching brackets to form pairs. The algorithm should correctly identify these cases and handle them as needed. Another edge case is an empty string, represented by. Since there are no brackets, no swaps are required, and the algorithm should return 0. The efficiency of the solution comes from directly tracking the imbalance without simulating swaps, which significantly reduces computational overhead. By making only one traversal of the string, the algorithm ensures that the solution is optimal and scales well even for large inputs. Finally, the implementation of the algorithm concludes by calculating and returning the result. After traversing the string and updating the counters, the minimum number of swaps required is determined as imbalance plus 1///2. This formula works because each swap resolves two unbalanced brackets, one opening and one closing. By efficiently tracking the imbalance throughout the traversal and performing this single calculation, we achieve an optimal and concise solution. This ensures that the algorithm not only handles all edge cases but also runs in O(n) time with O(1) space, making it highly efficient for balancing strings of any length. This implementation solves the problem by calculating the minimum number of swaps required to balance the given string. The key insight is to count the number of unmatched closing brackets and determine the imbalance caused by them. We start by initializing two variables, imbalance, which tracks the number of unmatched closing brackets, and closing_brackets, which counts the current number of unmatched closing brackets as we traverse the string. As we iterate over the string S, if we encounter an opening bracket, we check if there are unmatched closing brackets, closing_brackets 0. In such a case, this opening bracket can balance one of the unmatched closing brackets, so we decrement closing_brackets. If no unmatched closing brackets exist, we increase the imbalance counter, as this is creating an imbalance. If we encounter a closing bracket, we simply increment the closing_brackets counter, as it represents an unmatched closing bracket. At the end of the traversal, the imbalance variable will hold the total number of unmatched closing brackets that cannot be balanced by any opening brackets directly. The minimum number of swaps needed to balance the string is given by imbalance plus 1///2, as each swap can fix two unmatched brackets at a time. This approach runs in O(n) time, as we only perform a single pass through the string, and it uses O(1) space since no additional data structures are required. The solution is efficient and directly addresses the problem's requirements. This is the Java implementation of LeetCode problem number 1963, minimum number of swaps to make the string balanced. The logic mirrors the Python solution, utilizing counters for imbalance and closing brackets to determine the minimum swaps required. Key differences include type declarations for variables and the use of Java's enhanced for loop for iteration over characters in the string. Let's walk through the first example where the input string is. Initially, we set two variables, imbalance and closing_brackets, both to 0. Starting with the first character, which is a closing bracket, we increment closing_brackets since there's no matching opening bracket yet. This updates the state to imbalance equals 0 and closing_brackets equals 1. Moving to the second character, which is an opening bracket, it matches with the unmatched closing bracket, so we decrease closing_brackets by 1. Now, the state becomes imbalance equals 0 and closing_brackets equals 0. For the third character, another opening bracket, there are no unmatched closing brackets to pair with, so we increment imbalance. At this point, the state updates to imbalance equals 1 and closing underscore brackets equals 0. Next, we evaluate the fourth character, which is a closing bracket. Since it doesn't have a matching opening bracket, we increment closing underscore brackets. The state now becomes imbalance equals 1 and closing underscore brackets equals 1. For the fifth character, an opening bracket, it matches with a closing bracket, so we decrement closing underscore brackets by 1. The state updates to imbalance equals 1 and closing underscore brackets equals 0. Finally, the sixth character is another opening bracket, and since there are no unmatched closing brackets, we increment imbalance. The final state is imbalance equals 2 and closing underscore brackets equals 0. To calculate the minimum swaps required, we use the formula, imbalance plus 1, divided by 2. With an imbalance of 2, the result is 2 plus 1, divided by 2, which equals 1. Therefore, the output is 1. Now, let's analyze the second example where the input string is. We start with initial values of imbalance equals 0 and closing underscore brackets equals 0. For the first character, which is a closing bracket, we increment closing underscore brackets as it doesn't have a matching opening bracket. This updates the state to imbalance equals 0 and closing underscore brackets equals 1. For the second character, an opening bracket, it matches with the closing bracket, so we decrement closing underscore brackets by 1. The updated state becomes imbalance equals 0 and closing underscore brackets equals 0. The third character is another closing bracket, so we increment closing underscore brackets again. Now, the state is imbalance equals 0 and closing underscore brackets equals 1. For the fourth character, which is an opening bracket, it matches with one of the unmatched closing brackets, so we decrease closing underscore brackets by 1. This results in a final state of imbalance equals 0 and closing underscore brackets equals 0. Using the formula to calculate the minimum swaps, imbalance plus 1, divided by 2, we find that with an imbalance of 0, the result is 0 plus 1, divided by 2, which equals 0. Therefore, the output for this example is 0. Moving on to the third example, the input string is. Again, we start with initial values of imbalance equals 0 and closing underscore brackets equals 0. For the first character, which is a closing bracket, we increment closing underscore brackets. This updates the state to imbalance equals 0 and closing underscore brackets equals 1. The second character is another closing bracket, so we increment closing underscore brackets again. The state now becomes imbalance equals 0 and closing underscore brackets equals 2. For the third character, yet another closing bracket, we increment closing underscore brackets once more. The updated state is imbalance equals 0 and closing underscore brackets equals 3. Next, the fourth character is an opening bracket, which matches with one of the unmatched closing brackets, so we decrement closing underscore brackets by 1. The state now updates to imbalance equals 0 and closing underscore brackets equals 2. For the fifth character, another opening bracket, we reduce closing underscore brackets again by 1 as it matches with another closing bracket. The state is now imbalance equals 0 and closing underscore brackets equals 1. Finally, the sixth character is another opening bracket, which matches with the last unmatched closing bracket, so we reduce closing underscore brackets by 1. The final state is imbalance equals 0 and closing underscore brackets equals 0. To calculate the minimum swaps for this example, we again use the formula, imbalance plus 1, divided by 2. With imbalance equal to 0, the result is 0 plus 1, divided by 2, which equals 0. Therefore, the output for this example is 0. This concludes the walkthrough of the examples, showcasing how we track the imbalance and unmatched closing brackets to determine the minimum swaps required to balance the string. The time complexity of our solution is determined by how we process the input string. The algorithm processes the string s in a single traversal, meaning we loop through each character exactly once. This traversal contributes n to the time complexity, where n is the length of the string. Inside this loop, we perform constant time operations for each character. For example, checking whether the character is an opening bracket or a closing bracket is an O1 operation. Similarly, updating the closing underscore brackets counter or adjusting the imbalance counter also takes O1 time. Since these O1 operations are performed for each of the n characters, the overall time complexity of the solution is O(n), making it highly efficient for larger input sizes. Now, let's analyze the space complexity of the solution. The algorithm uses constant extra space, which means the space required does not grow with the size of the input string. Specifically, we only maintain two integer variables, imbalance and closing underscore brackets. Both of these variables require O(1) space each. The input string s is provided as input and does not contribute to extra space since we are not creating any additional data structures or performing recursive calls. Because the algorithm avoids using arrays, stacks, or any other structures that scale with n, the overall space complexity is O(1). This constant space usage is a key advantage of this approach, as it ensures minimal memory consumption regardless of the input size. To further appreciate the efficiency of this solution, let's compare it to a brute force approach. In a naive method, we might repeatedly scan the string to identify misbalanced brackets, perform swaps, and repeat this process until the string is balanced. This would involve scanning the string, which takes O(n), and performing multiple passes to fix all imbalances. In the worst case, this repetitive process could result in a time complexity of O(n squared). In contrast, the optimized solution avoids these repeated passes by calculating the total imbalance in a single traversal and directly determining the minimum number of swaps. The key insight here is that one swap can fix two misbalanced brackets, so the number of swaps required is exactly half the total imbalance. This is calculated efficiently using the formula imbalance plus 1/2, which ensures the result is accurate even for odd imbalances. This mathematical approach eliminates unnecessary computations and highlights the optimality of the solution. Finally, let's examine the best, average, and worst-case scenarios for this algorithm. In the best case, the string is already balanced. Here, the loop still processes all n characters, but no swaps are required. The time complexity is O(n), and the space complexity remains O(1). In the average case, where the string is randomly imbalanced, the loop again runs O(n) operations, and calculating the imbalance is O(1), leading to the same overall time and space complexities. In the worst case, the string is maximally imbalanced, such as having all opening brackets, followed by all closing brackets. Even in this scenario, the algorithm processes all characters in O(n) time, and the imbalance calculation remains O(1). Therefore, the solution consistently achieves O(n) time and O(1) space, regardless of the input, making it robust and scalable for any input size. When solving this problem, there are a few common mistakes to watch out for. First, it's important not to confuse swaps with reversals. A swap simply exchanges the positions of two brackets, whereas a reversal changes the order entirely. Misunderstanding this distinction can lead to overly complex or incorrect solutions. Next, don't forget to handle edge cases, like when the string is already balanced. For example, a string such as doesn't require any swaps, so performing unnecessary computations here wastes time. Another frequent issue is using nested loops to count imbalances, which results in an inefficient O(n squared) solution. Instead, aim for a single pass approach, such as a greedy or stack-based strategy, which is much faster. Additionally, be cautious with the balance counter. Ensure it's updated correctly increment for and decrement for, and avoid letting it go negative, as that would indicate an imbalance. Lastly, remember that the problem guarantees an equal number of, and, so you don't need extra validation checks. Ignoring this constraint can lead to unnecessary complexity. Now, let's focus on some key insights and variations often discussed during interviews. The essence of this problem lies in managing the balance of brackets. The balance increases when encountering and decreases with. If the balance ever goes negative, it signifies an imbalance that requires correction via swaps. The optimal solution uses a greedy strategy with a balance counter. As you traverse the string, track the minimum balance. The number of swaps needed can be computed as the ceiling of half the absolute value of this minimum balance. Recognizing patterns is also crucial, as this problem is a variation of the classic parenthesis balancing problem, a common theme in stack-based questions. Interviewers may also ask follow-up variations, such as minimizing the total cost of swaps when each swap has an associated weight. This shifts the problem into the realm of dynamic programming. Related problems include LeetCode number 921, which focuses on counting extra parentheses needed to make the string valid, and number 1249, which involves removing invalid parentheses. Other examples include number 1541, which requires insertions to balance a string, and number 20, a foundational problem on validating balanced parentheses. Finally, let's explore some alternative approaches and their trade-offs. One method is the two-pointer approach, which involves identifying and swapping mismatched brackets. While intuitive, this method is less efficient and can be challenging to implement cleanly. Another option is the stack-based approach, where a stack is used to track unmatched brackets. This simplifies the process of managing imbalances, but it comes with an additional space complexity of O(n). The most efficient solution is the greedy balance counter approach, which operates in O(n) time an O(1) space. By directly counting imbalances and calculating the required swaps, it avoids the overhead associated with stack usage. However, each approach has its trade-offs. The greedy method is faster and more memory efficient, but it demands careful handling to avoid mistakes in implementation. On the other hand, while stack-based solutions are easier to understand and debug, they're less optimal for scenarios with large inputs. Choosing the right approach depends on the constraints and requirements of the problem at hand. Great job! To recap, we solved the problem of balancing a string with the minimum number of swaps using an efficient two-pointer approach. This problem reinforced the importance of understanding string manipulation and optimizing for time and space complexity. Be sure to practice similar problems to solidify these concepts. Thanks for watching, and don't forget to like and subscribe for more. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!